Hello, my name is Ben Cohen and I am a 3B Nanotechnology Engineering student. For my final project, I will be introducing and analyzing grayscale electron beam lithography for three-dimensional patterning and discussing various experiments completed using this technology. As an outline for this presentation, first I will quickly introduce the concept of electron beam lithography, or EBL for short, as well as grayscale EBL. Then I will move into discussing a few completed experiments where I will examine and analyze the fabrication involved for three-dimensional structures for varying applications. Then I will dive a bit deeper into how GEBL works against alternative methods of fabricating three-dimensional nanostructures. And lastly, from these experiments and comparisons, I will analyze its usage potential and outline the next steps in its development. In this section, I will explain what both electron beam lithography and grayscale electron beam lithography are. Electron beam lithography is a pixel-by-pixel direct writing technique used for small-scale nanostructure fabrication. It works by scanning a focused beam of electrons onto a resist surface. The electron energy breaks the bonds of the resist, changing its solubility. This schematic is visualized in the image on the left. EBL is a promising lithography technique and widely thought of as the next method to be used for high-volume IC manufacturing. However, EBL is currently limited by slow throughput, charging while working with insulating materials, and the proximity effect from electron scattering. The proximity effect is shown on the image on the bottom right, where we can see that the electrons can penetrate deeper into a material, influencing the spatial dosage. The key idea behind grayscale electron beam lithography is modifying the exposure dose spatially across a resist. This can be achieved by tailoring the exposure time or incident electron energy. This gradient in exposure creates a differential solubility among different spatial regions in the resist, which upon development yields varying depths, creating the three-dimensional pattern. Because EBL is a direct writing method which exposes the resist pixel by pixel, it allows the user to directly control the dose applied at each pixel to create highly specific structures. This process is called shot modulation. One important limitation to consider while implementing a GEBL strategy to fabricate three-dimensional patterns is the proximity effect from electron scattering. This spread in energy may lead to undesired exposure in the surrounding pixels. Because of its ability to produce unique structures with high resolution and with low surface roughness, GEBL is a strong technique to fabricate complex three-dimensional patterns. Now that we have a general understanding of what EBL and GEBL are, let's dive into some specific experiments to examine its wide capabilities when it comes to patterning complex three-dimensional structures. I will first start by explaining two examples which demonstrate the general patterning technique to form three-dimensional nanostructures. Then I will show two applications to fabricate optical material and processes, and lastly I will dive slightly deeper and discuss its uses in integrated photonics. A rather simple first example, this group implemented a grayscale EBL and thermal annealing process to fabricate vertical and slope sidewalls. The thermal reflow step is a commonly applied post-processing technique to modify the geometry of a resist. Once the resist is heated past glass transition temperature, it experiences a change in viscosity which influences the surface energy. This change causes the surface to smoothen. This group capitalized on this property by considering the fact that PMMA's viscosity is significantly decreased upon annealing. Because of this, the reflow is highly selective and doesn't influence the surrounding unexposed area. This group implements a three-stage fabrication process which can be visualized on the image on the left. Firstly, after developing PMMA on a silicon substrate, they achieved the three-dimensional resist patterns by shot modulation. Then, they developed the resist, creating a step profile. Lastly, they thermally annealed the microstructure to create a slanted three-dimensional profile with a continuous slope. In the two figures on the right, we can see that the number of steps in the nanostructure and the annealing temperature influence the slope of the sidewall. This group's work focused on fabricating an array of asymmetric microidenticals, or tooth-like structures. These funnel-mimicking geometries have a smooth tapered sidewall with differing length scales on the x and y axes. The purpose of this work is to create a master mold for nano-imprint lithography using grayscale EBL. This work implements a TASTE mechanism, which stands for Temperature-Activated Selective Topography Equilibration. This technique involves grayscale EBL and thermoplastic reflow, a process very similar to that of the previous product. Via lateral shot modulation, this group was able to create molecular weight variations in the respective axes. The larger the exposure dose, the more bonds are broken, which results in a lower molecular weight and therefore higher development rate. By controlling the temperature and exposure dose, this group was able to finely tune the structures they fabricated. They attempted two process variants, positive or convex geometries and negative or concave, which is shown in the two leftmost figures. The negative process displayed a higher stability due to a larger stabilizing area surrounding the exposed regions. By first fabricating a staircase profile via pixel-by-pixel EBL and then thermal reflow, they were able to make a high aspect ratio tapered sidewall with a continuous slope and a PMMA resist. Simply, to create the two separate x and y height gradients, they step laterally across the two axes via shot modulation, resist development using MIBK, and thermal reflow. So now that we've seen some basic fabrication techniques using GEBL, let's investigate its use in optical applications such as lenses. Cuneiform lenses are lenses which can be used to focus X-ray radiation from a synchrotron beam. Though these lenses have high-quality imaging capabilities, they are extremely difficult to fabricate. Using GEBL, this group attempted to fabricate a three-dimensional profile into a SML 2000 positive resist. Due to the highly complex geometry, this group used a Beamer tracer software to run Monte Carlo simulations to modulate the applied spatial dose. After spin coating the resists onto a silicon substrate, the resists were exposed to an electron beam using the calculated dosages from the simulation. This simulation output three different dose spatial patterns, type 1, type 2, and type 3. All three patterns require proximity effect correction, though based on the actual results, type 2 had the optimal output. Pattern 1 follows a sharp profile, which requires a smooth tapered sidewall. Type 3 is quite different, needing an almost vertical sidewall. From the dose profiles, we can see that type 2 is an intermediate between types 1 and 3. We can see that type 2 is the best option, which can be attributed towards a limited resist contrast. The simulated dose distribution and the actual resist profile are shown in the bottom two images. After exposure, the resists were developed using IPA H2O in a 7:3 ratio for 4 minutes. Then, gold was electroplated into the resist profile, making the lens. This process flow is shown in the image on the top. Taking advantage of the high degree of control and precision involved with GEBL, this group was able to create a cuneiform lens capable of focusing X-rays into nanoscale spots with object magnification. Many large IC manufacturers are turning towards implementing deep or extreme UV lithography techniques to pattern their integrated circuits, though many smaller companies cannot afford the expensive equipment required to use this technology. Instead, there has been major research efforts for focusing beyond the diffraction limit, with one approach being using the photon nanoject effect in dielectric microspheres. To optimize the design of this lens, they implemented a finite difference time domain algorithm in combination with a Monte Carlo simulation to modulate the spatial charge distribution for grayscale lithography. To start the fabrication process, they spun coat a 1.45 micrometer coating of PMMA on a silicon wafer. Then, using the simulation results, they used Grayscale EBL to create the lens profile and the resist. The dosage profile and PMMA predicted template output are shown in the figure on the left. After developing this profile using IPA H2O in a 7:3 ratio, they casted a 500 nanometer thick coating of SU8 on this pattern area via spin coating and separately spun and coat another 500 nanometers of SU8 on glass. Then, they bonded the two wafers together and lift off the SU8 from the PMMA by dissolving the PMMA in acetone. This left a nanolens attached on glass. This fabrication schematic is shown on the bottom of this slide. Now that we've investigated some GEBL applications for optical materials and processes, let's look into some integrated photonics. Gallium nitride is a 3,5 direct bandgap semiconductor often used in blue light emitting diodes. Recently, many groups worldwide have been implementing GEBL as a fabrication tool to create these three-dimensional structures. Although gallium nitride-based LEDs are already commercially widespread, there are large efforts to improve its optoelectronic properties. One method to improve such properties is patterning the gallium nitride layer on a sapphire substrate with the quantum wells. This is implemented to minimize the number of trap states and mediate the thermal expansion gradient between the inorganic semiconductor and ceramic. After fabricating their device on the substrate, they spun coat a 100 nanometer thick coating of MAN2401, which is a negative EBL resist. Then, they exposed the resist with a 100 kV 0.3 nanoamp electron beam. To achieve the quantum well resist pattern, they exposed the resist 5 times with an overlapping dosage, increasing from the corners to the center of the triangle. This is visualized in the schematic on the bottom of the slide. After exposure, the resist was developed using TMAH. Then, the samples were etched via inductively coupled plasma to translate the pattern into the gallium nitride layer with either a 100 or 200 nanometer pitch. Then, they deposited a gallium nitride buffer and an indium gallium nitride layer. This patterning achieves a topography which mimics that of a quantum well. This process can be visualized in the top schematic. These patterned and deposited quantum wells provided a net increase in the photoluminescent properties of the semiconductor. Fabry-Perot interferometers are optical cavities with a maximum optical transmission at wavelengths which are integer multiples of the mirror spacing. By placing PMMA in between two metal plates, it forms a Fabry-Perot cavity. Here, aluminum and nickel act as the mirror. Fabry-Perot cavity colors are strongly related to the cavity length, or in this case, the thickness of the PMMA layer. By directly exposing the resist to an electron beam, it undergoes shrinkage. This group capitalized on this effect by creating spatial patterns in the z direction by modulating the exposure dose. This local thinning of the exposed region, which is directly related to the exposure dose, moderates the cavity color. Higher dosage induced more shrinking in the resist. This is visualized in the two leftmost images on the slide. By having fine control over the color emission, this group was able to make unique patterns which are shown in the image on the bottom right. There was no resist development needed in this technique. Now that we understand the working principle behind GEBL, it is important to compare the alternative three-dimensional patterning methods to analyze its potential and scalability. Stereo 3D lithography and two-photon polymerization is a direct writing massless photolithography process. Here, light with a specific wavelength is pulsed at a photosensitive polymer. This initiates the polymerization process of the exposed regions. Layer by layer, this additive process can create three-dimensional structures, though the resolution of these processes are much lower than EBL and is geared towards only polymers. There are similar techniques for metals, including laser powder bed fusion, though again the resolution is much worse than EBL. Nano-imprint lithography is a mechanical method for nanoscale feature patterning by using a mold. This technique provides elite resolution, demonstrating feature sizes below 10 nanometers. Though this technique can be used to mold very small nanostructures, it often requires EBL patterning for mold fabrication, which can take months. Mold fabrication can become very tedious and may have a short lifetime. Also, it isn't a great method for producing large area devices, but neither is EBL. Lastly, nanophaser lithography is a direct write grayscale technique which is easier to control than EBL. The equipment itself is much cheaper than traditional EBL equipment. This direct writing, massless technique is a non-invasive process which is also Goldbach's compatible. This fabrication is actually more promising than EBL, but is also a very new technology and not as widely implemented or known worldwide. Now that we've explored the principles of grayscale, EBL, analyzed multiple fabrication techniques for varying applications, and compared it to its alternatives, it is important to outline its potential and next steps as well as its overarching limitations. In this presentation, we've only examined a few of the countless applications of GEBL lithography. Although very slow and complex, this technique can be used to fabricate very specific and highly detailed three-dimensional nanostructures. This technique's precision and high resolution makes it very promising for various fabrication applications, though its potential is significantly hindered by its low throughput, inability to work on insulating materials, and the proximity effect. Though the proximity effect can be mitigated by incorporating correction factors in the design. So as a final statement, GEBL can definitely become the next generation of mass production three-dimensional nanostructure fabrication, though many advances in its scalability must be made before its incorporation in these fields. Here is a list of all the citations used in this PowerPoint. Thank you for listening, and I hope you learned something new.